Yeah. So yeah, my name is Baptiste Ruffio. I go by JB. So I'm a postdoc at Caltech. So my plan is to give you a status update of a new instrument that we have been working on. I guess not so new anymore, but called KPIC, which stands for the Keck Planet Imager and Characterizer. So it's led by Dimitri Mawet, Caltech. It's obviously a team effort. So everyone is on this slide. So I'm just a messenger. So KPIC was actually a pretty exciting development because KPIC is the first instrument of its kind to come online. And the idea was to combine two otherwise mature technologies, which are high contrast imaging to image and detect planets and brown dwarfs, companions, and high resolution spectroscopy. So KPIC does that at a resolution of 35,000 in K-band, but we have plans to expand that to L-band and also shorter wavelength. So why is doing high resolution spectroscopy of direct image planets so hard is because of this. Planets are faint, stars are bright, and planets are close to the star. So on the left, you have the 4 HRC 8799 planets orbiting their star. And each image in that movie is heavily processed. And so it combines 1 hour of data, and each raw image had the stellar PSF had to be subtracted from each raw image because a raw image looks like the one on the right. And so to give you an idea, the enormous planet is about a few % of the starlight at its separation. So, and yeah, so it's the regular spectrographs were not designed to do this. So here's come KPIC. So KPIC is not technically a new, I mean, it's not really a new instrument. It's more of a series of upgrade to the Keck 2 instrument suite. So it included a pyramid wavefront sensor that was commissioned a few years ago, so that's working very well, but I'm going to focus on the fiber injection unit. So the idea is that we take a single mode fiber, we pick up the light, the output of the adaptive optics, and then feed the NIRSPAD spectrograph with it. There are several advantages to the single mode fiber. So the first one is that it gives you a very stable line spread function. So very stable calibrations if you want to measure spin or do Doppler imaging, that's very good, very good. And the other one is that it helps us suppress the starlight. So because it's a single mode fiber, only the planet light will couple well with the fiber, and the starlight won't as much compared to like a slit spectrograph, for example. So here's a rough timeline of the project. So it started 2017. So we commissioned the fiber injection unit early last year, and got our first detections. And we have been doing science for the past year. We're actually already reaching the end of phase 1. So we have several upgrades that I'm going to mention at the end, planned for early next year. That also including a laser frequency comb. And all of these are paving the way for the next generation instrument, like a high spec. So why do we need high spectral resolution? So these slides like summarizes the couple science cases that we're thinking about with KPIC. And so for each science case, I've like shown like the effect on the spectrum. So this is just the CO band head around 2.3 microns, and the effect on the cross correlation function. So the cross correlation functions are the typical type of analysis that we do on high resolution spectra. The idea is that you take a template, like a spectrum template, and you shift it as a function of the like with a radial velocity shift, and you fit that template for every shift, and you get that function. So if you have a peak, you have a detection. So yeah, so we want to measure radial velocity of companions, so planets, their spin from the width of the line. An exciting science case that we're trying to commission as well that is Doppler imaging. So if you have some intensity variation at the surface of the planet that comes in and out of view like a cloud, that's going to affect the spectral lines, and we hope to be able to detect that. I mean, that has been done, but we hope to be able to do that for higher contrast objects. And last but not least, we want to constrain atmospheric parameters, and in particular, because the high resolution can resolve molecular lines, we're more sensitive to abundance measurement, like to the abundance of these molecules. So in K-band, it's going to be water and carbon monoxide. And all of these are like, if we take measurement of like radial velocities, that's going to help us constrain the eccentricity of these planets. Or if we measure so eccentricity, spin, or the carbon to oxygen ratio of a lot of planets, we hope to tie that back to planet formation. that's a big picture. So here's how KPIC works, very roughly. So we have 4 fibers on the line. So we need to place one of these fibers very precisely at the location of the planet. So we need to know where it is. And then we try to align the other fibers such that at least one samples a starlight. So this is just a small part of the detector. So on NeurSpec, you get 9 orders to cover the entire K-band. And for each order, we get a trace for each fiber. And so we implemented our own custom-made pipeline to do optimal extraction and get calibrated spectra for these. One such spectrum is like the one at the bottom here, and I've added some templates for comparison. So on top, so we don't telluric normalize. I mean, we don't divide by the telluric spectrum. We try to forward model everything. So, but on top, you have the transmission spectrum, so including the instrument and the tellurics. You have a water template and a carbon monoxide template in the middle. So water is more at the beginning of K-band, and this is towards the end. So this is more carbon monoxide. And you also have a Brandorf template, because this is Brandorf data. And the thing you have to realize that because we observe companions, high contrast companion, we actually need to model both the starlight and the planet light together in order to feed our data. So this is a Brandorf that's fairly bright and fairly separated. So the starlight is like 1/10 of the light of the Brandorf. So that's an easy case. But we have these 2 models. We define a likelihood, we forward model everything, and we feed our data. So if we shift the companion model, we can get something that looks like a cross-correlation function. So this is not your typical way of calculating a cross-correlation function, but yeah, this works. So I said that the Brandorf I just showed you is an easy case, but for the HR 8799 planets, for example, the starlight is many, many times, like 10 times, 20 times brighter than the planet, but we still can detect them in a couple hours. So this is work done by Jason Wang that was accepted a few months ago, I think now. So each panel contains the posteriors for each of the 4 planets. So on top left, you have the radial velocity measurement. Our measurements are consistent with the orbital, the predicted orbits. Top right, you have the spin measurement of these planets, which were the first spin measurements for these planets. So this was fairly exciting for us. And at the bottom, you have a measurement of effective temperature in log G. So obviously, this is just using KPIC data, and KPIC is not the ideal instrument to do this, but we can still show them. So if we put the spin measurement of the HR-99 planets and compare them with other Brandorf companions, we realize that these planets actually spin quite fast, up to 40% of their breakup velocity. So the difference between the left panel and the right panel is on the right, the spin axis is assumed to be random, and on the left assumed to be a line, I mean, perpendicular to the orbital plane. So we think there's a tentative trend there. So obviously not confirmed, but we hope that with KPIC, we can add more data points at the lower mass end and actually confirm if this trend exists or not. And that would be consistent with the magnetic braking from the circumplanetary disk during the planet formation, which would probably be less efficient at lower planet mass. So we're doing a survey. Yeah. So here, we have about 20 detections so far. We have another 6 nights waiting for us next semester. But I don't have much more to say on this slide. So I'm not going to talk about this one a lot because Jerry has a talk tomorrow. So I'm going to refer you to his talk around 12:15, if I'm correct. So talking about the atmospheric characterization using this high resolution data. So we have several data sets, several people working on them. So stay tuned for the result that's going to come. So I mentioned earlier that we are reaching the end of phase 1. So we have a couple of grades planned for early next year. First one, a beam shaping optics to improve the coupling with a single mode fiber, so improve our throughput. An atmospheric dispersion corrector to correct for the atmospheric refraction, a higher order deformable mirror to get better Strel, and so better coupling, better throughput. So the throughput and the thermal backgrounds are the main issue for us. So any improvement or either is really important. And an exciting new mode too is the vortex fiber nulling. So I'm going to refer you to Dan's poster in session B. So the idea is to be able to detect planets at between 0.5 and 2 lambda over d. which is super close, like an unexplored territory. So this would allow KPIC to not only characterize known planets, but detect new ones and ones that we would not be able to detect otherwise. So there's also going to be a laser frequency comb installed, and high spec in several years. And this is it. So yeah, I put back the timeline if you want to look at it. Thank you. And I'm going to take any questions. So the question is about, do we have any plans to bring KPIC to visible light to detect radial velocity planets? Is that right? Like RV, yeah. I think visible light would be a stretch. So we have plans to bring it to like shorter wavelengths, but still in infrared. I don't think the adaptive optics, everything would work well in the visible. For example, something like the vortex fiber nulling might allow us to detect some radial velocity planets, TBD, or we're looking into that, for example. Oh, sorry. Andy, can you speak and give your question?
Yeah, so Andy Shane is here at CFHT. I'm curious about the laser frequency comb and what the plan is. Is this going to be for simultaneous observations with the laser frequency spectrum laid directly underneath the planetary spectrum?
Yeah, so the idea is to have it on one of the fibers. Yes.
To have it on one of the fibers. And do you know which laser frequency comb are you folks planning to install?
I might not be the best person to answer the question.
Okay.
So okay, I would suggest you can write the question in the Slack chat, and then I'll refer to the right person to answer that.
Okay, thank you.
Bruce.
Yeah, right.
Hi, Bruce.
Hey, JB. Actually, I had another laser frequency comb question. Is the goal to get precision velocities of the host stars to become a Doppler planet finder, or just to do a better job of measuring the velocities and maybe the spectra of the planets? What are the science drivers for the laser frequency comb?
I think all of the above, really. I mean, yeah, doing some high precision radial velocity in infrared, definitely, but also like getting a really good line split function if we want to do Doppler imaging or even measure spin, that's going to be really critical. So yeah.
Okay. All right. Time for one more. Chaz has a question. So you can tell him.
Hi, Chaz. Actually, Chaz, if you want to answer the laser frequency comb questions, please by all means do it.
Yeah, just can you hear me? Yeah, really quickly. Yeah. I mean, we've got a laser frequency comb that runs from, J and H band. We're working to extend that to cover or Y through K, probably two combs working together. And we have a Heising-Simons Foundation grant to put that onto NERSPEC over the next year, led by Stephanie Life, was at JPL, now at Aerospace, myself, Dimitri Mawe, a number of other people are involved. And the goal is both, precision RV at the few meter per second level. Now, NERSPEC is only RF 35,000, as well as JB said, provide, samples of the line spread function, every few nanometers.
Thank you, Chaz.
Okay. Thank you, JB again.